Now, one of my friends had provided me with an assignment work on the mathematical methods of physics, and I tried out a few of them, and I would like to discuss them. I would rather not talk about what I couldn't do, but I would share a few numericals which may help us in understanding the mathematical methods in physics, the topic, in a better way. So let's start with it. To start with, it consists of two parts, of course. The first part, part A, has the first question as this. That is, we need to solve this given equation using the separation of variables. This is a partial differential equation, and we have an initial condition that u at x comma 0, that is for t being equal to 0, because we know that from the differential equation that u is depending on x and t, so the other variable is obviously t, so u at x0 is equal to 3e raised to the power minus 3x, that is the exponential uh, raised to the power minus 3x. So in order to try this, the solution involves the separation of variables. So what we do is we consider u of xt to be consisting of two parts. One, depending on x, let us take that as phi x, while the other, let us take that as psi t. You can take any variable you wish to. So now we have del u over del x to be equal to, because this is the partial derivative, so psi t is constant in that case, and we end up with del phi x over del x. Similarly, for del u over del t, we have the factor on the right hand side that we see with the function given. We have 2 times of phi x times of del psi t over del t. So this is more or less the case. So taking this equation into account that we have with us, del u over del x giving me this value, we can take it in the left hand side of that equation. So for del u over del x, so we have psi t del psi x over del x, and for the right hand side, del u over del t. Well, actually, del u over del t won't be having that 2 because we will be using that 2 in this equation, so this 2 remains, comes up over here, and del u over del t is simply phi x times of del psi t over del t. And for the last case, last bit, we have the value of u that we are going to put as phi x psi t that we have taken the form. Now all of this can be divided with this last term, that is phi x and psi t. So dividing the entire equation by the factor phi x psi t, that is obviously equal to u. So what we have is, on the left hand side, psi t gets cancelled, and what we are left with is only 1 upon phi x and del phi x over del x. And on the right hand side we have 2, the phi x values get cancelled, and we are left with psi t in the denominator, and that multiplied to del psi t over del t, plus this quantity goes to 1. Now all of this, because we have separated the variables, we can just take them to be equal to some constant value, let that be equal to k. So what we have essentially is that this first part will be equal to k, and also the second part that we have, both of them will be equal to k independently. So we get, now because we have separated them, we can take the complete derivative. So d phi x over dx, and there was 1 over phi x over here, and that is equal to k. So what we get from this is that we have d phi x over phi x. The dx can be taken to the other side, so we have k dx over here, and integrating this thing would give me the ln of phi x, and on the right hand side that will give me kx plus some constant. Well, for this constant we can take it as ln c, because we have the logarithmic term on the left hand side, so it will be easier to compute. So we take that ln c onto the left hand side, and that's in the negative, that's a negative sign that will appear, and that will result in the entire logarithmic value to be ln of phi x over c, and that will be equal to kx. Now further, with if we wish to take the logarithm out of the equation, so what we get is phi x of c with the logarithmic expression converted to the exponential term, so we are left with e raised to the power kx. Or we can just take the c onto the other side, and we have phi x to be equal to c times of e to the power kx. So this is the expression that we get. We will be obtaining the value of those constant terms k, c, and all of that, because we need them to obtain the solution. We need to solve this. Now let's move over to the second case, where we are taking the second part of the equation on the right hand side, and we are equating with it with k. I'll try it over here in the space available. So for that, what we get is 2 over psi t plus 1, no, 2 over psi t del psi t over del t, and the 1 can be taken to the other side, so we are having k minus 1 onto the other side. Now because these have been separated, the variables have been separated, so it's easier, or it's apt to take the complete derivative instead of the partial one. So we are taking it as d psi t over dt, and we'll be trying the same method, that is d psi t over psi t, and this thing can go to the other side. We can take the 2 along with it as well. So k minus 1 divided by 2, and the other side we have dt. So this again integrated gives us ln of psi t on the left hand side, and here we have k minus 1 over 2 multiplied to t, plus we can take another logarithmic constant, let that be ln c primed. So that is c primed, just to make a difference. And from that what we get is, again we will be getting that same form, so I'm writing it directly. So psi t is going to be equal to c primed e raised to the power k minus 1 over 2 times of t onto the right hand side of the equation. Now with both these parts available, what we get is we will be using that in the value that we have at hand. Now we have u, we need to find u obviously. So u of xt will, being a combination of both of them, what we get is, so u xt now will be equal to the multiplication of both of them, as we had taken over here at the top, which is phi x times of psi t. Phi x carries a constant c, e raised to the power kx, and c prime is the constant in psi t, so let me write that first along with c. So c primed, and e raised to the power kx for the first term, and then we have the second term, so I'll take it as sum of the power terms, that is k minus 1 over 2 times of t. So that is giving me the expression for u, but it's not a complete expression. We haven't solved it completely yet. We'll be using that initial condition where for t is equal to 0, for x 0 as we know it, that is, we are putting the value of t is equal to 0 over here. So what we have is the value to be equal to 3e to the power minus 3x that has been given, and by putting that value, this t term in the power of the exponential, that goes to 0, and that completely erases the second part of that exponential power term, and we are left with just e to the power kx. So this is c primed e to the power kx, because the t is going to 0 and that second part of the power term is going to erase, and so that gives us, comparing both these sides, comparing, what we get is the value of c primed is just equal to 3, and that of k, which is multiplied to x, and that will be equal to minus 3 while comparing it with the left hand side term. So we have the constant values that we wish to obtain, and now we can put them in the above expression that we have collected over here, and so the final expression u of xt, which was to be obtained, is equal to c prime, remember, is 3, e raised to the power k is also having a value of 3, but we'll minus 3, of course, minus 3x, and k minus 1, so that is minus 3 minus 1 is minus 4 over 2 is minus 2, so this is minus 2 times of t, and we can just take the minus term as common, so we have 3 e raised to the power the negative of 3x plus 2t. So that's our solution that we are looking for. This is the answer. So let's move over to the next question. So in the next question, it asks us to consider a rod of length L where the ends are kept at a constant temperature and its lateral surface is insulated. The heat flow is described by one-dimensional heat diffusion equation subject to the conditions that for f at 0t, that is the beginning of it, for the length being 0, so the starting point, or we can say one end of the rod, and for f at lt, that is the other end of the rod, considering the length of the rod being L, that is equal to 0 at any given time t greater than 0, which is at any given time, of course. And for taking f of x0, that is for t is equal to 0, we are having the initial condition that sine f of x0 is equal to the sine of 3 pi x over L, wherever we consider the length, wherever we consider the point for x lying between 0 to L. And we need to obtain a unique solution to that. Let's see what unique solution can we get. So the solution involves the consideration of one-dimensional heat flow equation, which is of the type the del F over del T is equal to c squared del square F over del x squared. So this is the equation for one-dimensional heat flow, which has been asked to consider. And in that case, what we are getting is that we again need to separate those variables, because that might be the case, or that might create a bit of problem for us. So f of xt again can be taken as two separate functions, as phi depending on x and psi depending on t. You can take any other variable or constant value instead of phi and psi, and the notation that is. And then we have the value of del f over del t. Well, I can write that directly now, having understood it in the first bit. So del f over del t is going to give me phi x on the left hand side multiplied to del psi t over del t, and then onto the right hand side what we get is the c squared term remains as such. In this we are using this equation for sure, and that gets multiplied to psi t, and we have del square phi x over del x squared. Again, that is equated to k, some constant. We divide this entire equation by f, that is phi x and psi t. So what we end up with is, because they have been separated, the variables have been successfully separated, so we can take the total derivative instead of the partial one. So, and on the left hand side, dividing by phi x times of psi t, what we get onto the left hand side, we have 1 over psi t d psi t over dt is equal to c squared over phi x d square phi x over dx squared, and that is equal to k. So for the first term, that is this one, it's fairly easy in this case. So we have that to be equal to, equating it to k, we get 1 over psi t d psi t over dt is equal to k. That is going to give us d psi t over psi t is equal to k dt, and on integrating this we end up with ln psi t is equal to k times of t plus we use another constant this time instead of c and all that, so we use ln a supposedly, and finally that's going to give us psi t is equal to a multiplied with e to the power kt. I hope you understand this part. I have skipped a step over there. Now this is the solution for the psi t part. We will be considering the phi x part for the rest of the case. As for phi x, well, this is double derivative, so what we are going to get is, we are going to get it in the form d2 phi x over dx squared, and the phi x and c square term can be taken to the other side, so we have and taking it back to one side, we have phi x k over c squared, and that is equal to 0. Now this equation would yield the solution of the form phi x will be equal to, we will have two constant terms over there, so we have c1 supposedly a constant, cosine of the root over of this term, so that is root k, and c squared under root is c, that multiplied to x, and as because sine, this is obviously a negative case, so we can put a minus sign over there within that bracket, but as you know, cosine function is an even function. We are going to do away with that minus sign later. So as for the second case, we have c2 sine, and again the negative of root k over c, and that multiplied to x, and this is the solution for phi x in this kind of an expression, where the expression is obviously of the form, that is d2 of any function, suppose f over dx squared plus this is omega squared. This is a wave equation that we are getting, so that is why we have this kind of solution, and this is equal to 0. So this is a harmonic function, the harmonic equation, and that as a result of that we are going to get the harmonic solution, which involves cosine and sine functions. So need not be worried about that. We have discussed this in our wave section. You can take a look at that. Else you can consider the higher secondary level physics, where we can get this kind of a solution. So as a result of this, we have two more constants, and also let me write that equation, because cosine, again I said, is a even function, so we are left with only root over of k over cx, and this one becomes minus, that is c2 times of sine root k over c times of x. Now with this value available to us, what we can write is for the conditions, we can move over to the conditions. Now the conditions state, the first of the conditions, that is this part, we are going to take the first part, that is for x is equal to 0, we have f is equal to 0. So for x is equal to 0, we have f is equal to 0, and putting the value 0 in each of those cases, in this expression especially, because there is no x term in psi t, so we are left with a combination. Let me write the combination of this first. So the combination f of xt is going to be phi x having the c1 and the c2 values, c1 cosine of root k over c times of x minus c2 sine of root k over c times of x, and that will be multiplied to psi t, which is a e to the power kt. So this is the entire function f xt, but for x is equal to 0, what we are going to get is we are just going to end up with the 0 on the left hand side for f is equal to 0. So we are putting this in this equation. So on the left hand side we have a 0, and that will be equal to, on the right hand side, for x is equal to 0, we have cos 0 to be 1, so we are left with c1 only in that entire square bracketed term, because sine 0 is going to give me 0, so the second term gets cancelled. And as for the a e to the power kt, that remains as such, so we have a e to the power kt times of c1. Well, a cannot be 0 over here, a can never be 0 because it has been chosen, so obviously the only thing that can be 0 over here is c1, so c1 from this value is obtained to be 0. Now, so what value of f remains? So f now has the value to be equal to, in that case, because c1 has gone to 0, that first term of the square bracket has been cancelled, so this cancels out completely, and what we are left with is only the second term, minus c2 sine of root k over c times of x multiplied to a e to the power kt. So we have f to be equal to minus of, well, let me write the a first, a e to the power kt, and the second term of the bracket where we have c2 sine root k over c times of x. Now we put the second condition over here, where for x is equal to L, we have f is equal to 0. So if this condition is put in the above value of f, so we are left with f being equal to 0, and on the right hand side we have a minus a e to the power kt c2 sine, and the term root k over c remains as such. For x we are having the value over here to be L. Now a again is not equal to 0, so a is not equal to 0, but the second term we cannot take c2 is equal to 0 because that will blow up the entire equation for f. So c2 cannot be taken as 0 over here. So what needs to be taken as 0 is the value of sine at that particular value, because sine is not having a variable x at this point. It is having a value L. It is involving the value L, so it is a fixed value, and at L, therefore it is going to 0. Now sine can be 0 at sine 0 and also at n pi. So in general, sine n pi is equal to 0. So obviously we have this value that is comparing, if we compare this term over here is equal to n pi. So root over of k over c times of L is going to give me n pi, and we are going to continue the rest of the problem in the next page. So now what that is going to give us is root k simply becomes equal to n pi, and the c can get cross multiplied to the other side, and that over L. Similarly, L gets cross multiplied. So we have the value of k to be equal to the square of these terms, that is n pi c over L, and squared completely. So f xt now has the general value as minus a c2 e to the power kt, and we are keeping the k for now. We are not using its value as of now. So sine n pi x, this is what the value of f looks like right now. Now we have another condition that for t is equal to 0, we have f to be equal to sine n pi x over L, and so we are going to apply that. So using this value onto the value of x, that is sine n pi x over L, for the value of f when t is equal to 0. Well, when t is equal to 0, the only thing that is going to be 0 is the power term of exponential, and that reduces the exponential to 1. So we are getting ac2, the negative of ac2 sine n pi x. This is what we are left with. Now the left hand side and the right hand side, obviously one is positive, the other one is negative, and therefore what we can say from this, we wish to obtain a unique solution for sure. So what we have is that AC2, the term AC2 therefore has to be equal to 1, and if that negative is taken within this, so we are left with AC2, and this is sine of minus n pi x. Now comparing, what we get is this is nothing but the minus can be taken like this, as this divided by minus 1. So what we are getting is a unique solution that L is minus 1 in this case. So that is the way of approaching this numerical, and therefore we have the final expression, and the final expression for f has the following value, that is AC2, as you know, is 1, so the minus term remains over there, and we are left with E. We are putting it over in this equation, so we are left with E. And as for k, we'll be putting this value that we have obtained for k, that is n square pi square c square over L square, right? And but there's one more thing to it, that L is minus 1, so we are getting this as minus of n pi c whole squared, so the minus becomes plus. Now we are left with n pi c square, and that has been multiplied to t, and we have sine n pi x. So this is the unique solution. Now you're open to any corrections regarding this. In case you find this to be something different from your answer, you're free to comment and rectify in case I have made a mistake. I don't think that it's wrong, but in case there is some error somewhere getting those values, you can always choose to rectify. Now the third bit in the series asks us to show the following Bessel's equation. Now the j2 prime x is going to be equal to 1 minus 4 over x squared j1x and plus 2 over x times of j naught, where j and x is obviously the Bessel function of the first kind. Now we have to use the recurrence relation. Now the recurrence relation involves mainly three formulas what we can relate. So the first formula, I'll be writing all those three formulas and we'll be using two of them to solve this. So the first formula involves, this is the first one, where we have the recurrence relation as x j primed n or jn primed to be equal to n jn minus x j n plus 1. So this is one form. Now why we are using jn plus 1? Because this involves this, as you can see, this involves j1. The above equation in the question involves j1, j0 and j2. So we have to choose an n for which we are getting all the possible relations, n plus 1, n minus 1 and likewise. Now the second formula involves the Bessel function to be of the form x jn primed to be equal to minus njn and plus x times of j n minus 1. So as you can see, these two formulas will be completely handy to obtain. We also have a third formula which again can be useful. So we have 2 jn primed to be equal to jn minus 1 minus jn plus 1. Well, as for this formula, what we may find a problem is that it does not involve x, it does not involve any number such as n or anything, so that may not help. So we will try with this equation, these two equations. We'll be using both of these to obtain the result. So let's see what we have. So if I were to consider the value of n in case of the second formula that we have, that is x j n primed is equal to minus of that. So this second one, we are using it first, and we are putting the value of n over here to be equal to, say, we are putting it as 2. Now putting this as 2, what we get is x j2 primed is equal to, on the right hand side we have minus 2 j2 and then plus x j1. This is what we get, and we can divide it with x, of course. Let's divide it with x. So j2 primed will be equal to minus 2 over x j2 plus j1, right? Then we use the first formula, and if we add it to the second one, the addition of both of these is going to give us, and I'm writing it over directly in this case, not the addition, actually we can compare it. So comparing, we can compare, and the left hand side obviously is the same, so the right hand side has to be equal, and so we have n jn minus x jn plus 1 to be equal to minus n jn plus x jn minus 1. Now we put the value of n to be equal to 1 over here, so what we get is Jn minus x j1, not 1 but 2, and here we have minus n goes to 1 and Jn is j1, and finally we have x j0. This is what we end up with. So having obtained this value by putting n over there to be equal to 1, we get the value of j2. Now j2 here will be equal to, what will be the value of j2? Now j2 with jn minus, did I write jn? Well, this is j1. So j1 minus, the minus becomes plus over here, so plus j1 minus x j0, and because x was multiplied to j2, we can divide this entire thing by x. So what we get is the value of j2 to be equal to 2j1 over x minus j0. This is the value of j2 that we have obtained. We'll be using it. So we use this value of j2 in this expression that we have, that is over here. So now using that value of j2, what we get is j2 primed to be equal to minus 2 over x, and for j2 we use that entire value, that is 2j1 over x minus j0, that is the value of j2, and plus there is j1 in that equation as well. So this is where we have used the value and j1 remains alone. So we have j2 primed to be equal to, this is minus 4 over x squared, so we are getting there, and j1 remains as such, and this one over here becomes plus of 2j0 over x, and lastly we have j1 over here. So j1 can be taken as the common term, so we have j2 primed to be equal to j1 taken as common, we are left with 1 in place of j1, minus 4 over x squared entirely multiplied to j1, and finally 2 over x j0 simply gives me the same result as that has been asked. Now the fourth one also involves the recurrence relation, but involves the Legendre's polynomial. So we have 6 formulas or 7 related to that, but we'll be using one of them, and I'll be giving that one formula that we'll be using for sure, and that involves the relation that we have. The recurrence formula is that we have 2n plus 1 times of p x times of pn. Pn is Legendre's polynomial, and Pn, and this is n plus 1 times of Pn plus 1 multiplied or added to n times of Pn minus 1. So with this formula, this is one of the recurrence formula, that we are going to use, and we'll be using different forms of it to obtain the value. So firstly we are going to replace n by n plus 1. So if we replace n by n plus 1, what we are going to get, in the first case on the left hand side, n plus 1 means 2n plus 2, so that is 2n plus 3, that is plus 2 added to 1 is 3, and here x, and over there we have Pn plus 1. On the right hand side we have n instead of n we are using n plus 1, so n plus 1 is n plus 2, and here we have n plus 2 as well, and this second term also has n plus 1 instead of n. N plus 1 minus 1 is going to give us Pn. Now we are going to replace n by n minus 1 in that same recurrence relation. So we are going to replace n by n minus 1 in the recurrence relation. So what that gives us is 2n minus 2 plus 1 is minus 1 x Pn minus 1, because you must remember that here we have Pn plus 1 and Pn minus 1, so that's important to us. And onto the right hand side we have instead of n, as we are going to use n minus 1, so we are going to be left with only n, and the p term that will consist of only n, and also the next term will have n minus 1 multiplied to p. N minus 1 is n minus 2. So this is what we are going to get by replacing the values with n and n minus 1 respectively. Now what we do is, let's take this equation as a, let's just take this equation as b. We are multiplying a with b now. So if we multiply a with b, what we get is, on the left hand side we are left with 2n plus 3 multiplied to 2n minus 1. The x terms get multiplied to give us x squared, Pn plus 1 multiplied to Pn minus 1, and onto the right hand side what we are getting is the terms are going to get multiplied, so n plus 2, so all of those terms, multiplying them one by one, we are going to get 4 terms in all. So firstly, n plus 2 multiplied with n, Pn plus 2 Pn. So this is the first 2 terms of both the equations. Now the first term of the first equation, second term of the second. So n plus 2, n minus 1, P n plus 2, Pn minus 2. The second term of the first multiplied to the first term of the second, that is n plus 1 times of n, Pn squared. And lastly we have the term where we are getting the last 2 terms of both those equations, n plus 1 multiplied to n plus 2 multiplied to Pn minus 2. So this is what we are getting after the multiplication. Now what we do is we wish to integrate this term from minus 1 to plus 1 over x. So on the left hand side we are left with, we can take the n terms out of the integration, so we are taking 2n plus 3 to n minus 1, and the integration involves x squared. Now because these legendary functions are obviously polynomials, are depending on x, so it's better to give an x to them, and this is dx, and this is from minus 1 to 1. Onto the right hand side of the equation what we are going to get is integration, so n plus 2 remains out, integrated from minus 1 to plus 1, Pn plus 2 Pn dx, plus the second term being n plus 2 n minus 1, integration minus 1 to plus 1, Pn plus 2 x, Pn minus 2 x. The third term, n times of n plus 1 or n plus 1 times of n, whatever it may be, Pn squared of x dx, this is dx, and this is from -1 to +1 as well. And the fourth term, n plus 1, n plus 2, -1 to +1 integrated Pnx, Pn minus 2x dx. Interestingly, we have the orthogonality property or orthogonality condition, which states that the integration from -1 to +1 involving Pnx with Pmxm and n for not being equal to one another, we have the value to be equal to 0. Now obviously n plus 2, n minus 2, n plus 2, n and n minus 2, all these terms, they will go to 0 following the orthogonality property. All we are left with is only one term, that is Pn squared. And so Pn squared integrated is going to give me, and the other part of the orthogonality property states that where n is equal to m, I'm writing it over here, for m is equal to n, we have the right hand side, that is -1 to +1, Pnx Pmx for m is equal to n, that is going to yield 2 over 2n plus 1. So this term over here is going to give me, on the left hand side we have 2n plus 1, not 2n plus 1, 2n plus 3, 2n minus 1, and integration of minus to plus 1, x squared Pn plus 1 x Pn minus 1 x dx is equal to, let me just separate the equations over here, and that is equal to, on the right hand side, because Pn square x dx has gone to this value, 2 over 2n plus 1, so we have n times of n plus 1 and a 2 multiplied to that over 2n plus 1. Now the rest of the terms on the left hand side over here can come up to this side in the denominator, so we have 2n plus 3 and 2n minus 1. So this, I think, was what we required at the beginning, and we are getting the exact value at the end. So that's proved. The last bit of the first question has the Hermite's polynomial, where we are to establish the relation that is given between hnx and hn of minus x. So as you know, this is Hermite's polynomial. We are going to get to the generating function, and then we are going to evolve or establish the relation between these two. So we have the generating function to be equal to gxt to be equal to e to the power 2xt minus t squared, and that is equal to the summation from n is equal to 0 right up to infinity hn of x t to the power n divided by n factorial. Now from this, what we get is g. If we take g of minus x and minus t, we simply end up as e to the power 2xt, that remains as such, and so does the t squared term, because the minus negative signs are going to get multiplied to one another and they are going to be positive. And as for the summation term, we have n going from 0 to infinity, and in that we have hn. For x we are using minus x over here, and t again is a minus t to the power n over n factorial. Now this has the left hand side remains the same, so we are not going to repeat it. As for the right hand side, what we can get is n taken from 0 to infinity has hn minus x, And as for that minus t, we can take the minus 1 out of that and take the power as n, and t to the power n over n factorial remains as such. Now if we are to compare the equations, this one and this one, so the left hand side remains the same, that is over here and over here the left hand side remains the same. The difference in the right hand side is with the hnx and hn minus x, the only difference being minus 1 to the power n. So we have hnx to be equal to minus 1 to the power n times of hn minus x, and this was the relation that we were to establish. Conversely, we can have also hn minus x to be equal to minus 1 to the power n times of hnx minus n instead of n. So this is the first question that we have solved. The second question now involves the matrices. It asks to obtain the eigenvalues and the corresponding eigenvectors of the matrix which is given over there, -2, 5, 4, 5, 7, 5, 4, 5, -2. Now that matrix, in order to obtain the eigenvalue, as we know that for a given matrix, let us take this as a solution involves us to take this matrix as supposedly A. So the eigenvalues is when we take A minus lambda times of the identity to be equated to 0, the determinant of that, and then from that we obtain the value of lambda, which gives us the eigenvalues. Now for that we take, obviously the A is that matrix over there, and A minus lambda times of I, well, this is -2. As you know, the I, that is the identity matrix, that is the diagonal matrix, so we have the minus lambda to be taken in these diagonal terms. So 2 minus lambda, 5 and 4, 5, 7 minus lambda, 5 and 4, 5 -2 minus lambda. This is, interestingly, this is actually a symmetric matrix, and let's see whether the eigenvalues that we obtain, they are repeated or non-repeated, because we have a condition that when the repeated eigenvalues and the non-repeated eigenvalues are obtained, then what do we have? So this is a symmetric matrix, of course, because as you can see, 5, 4, 5 in the top right corner and 5, 4, 5 in the bottom right corner, -2 in the left corners and the top right corner. So this is completely a symmetric matrix. So now this is equated to 0. Now the determinant of this, so determinant, let me erase that matrix symbol. That's the determinant. I've also provided the identity matrix, and when lambda is multiplied to that matrix, you have lambda and lambda in the diagonal, and that is subtracted from the A matrix that gives us minus lambda terms in each of those diagonal terms. So this is the determinant of this is taken to be 0. So let's calculate the determinant in the first place. So -2 minus lambda times of 7 minus lambda, -2 minus lambda, minus the other two terms, multiply to 25. So this is for the first one, -5 for the second case. I hope you know how to obtain the determinant in this case. So 5, and it involves 5 -2 minus lambda, and this is -20, and the place value for 5 being negative in that case, so I have taken -5. So now 4 multiplied to 25 minus 4 times of 7 minus lambda. This is to be equated to 0, and if you solve it, what you obtain, I'm writing it directly because I have tried it in my rough sheet. So I have a lambda cube minus 3 lambda squared minus 90 lambda minus 216. This is just to shorten the video so that it doesn't go till eternity. So this is more or less the case. Now the eigenvalues, while solving this, you can solve this in the synthetic division method. In case you do not know about that, we can discuss it in some other short video, that is the synthetic division for the polynomials that we are considering. Now from this, what we get is the value of lambda will be obviously having three values because the lambda cube. So lambda is having the value is going to have 12, minus 3 and minus 6. These are the values of lambda. These are therefore the eigenvalues of the given expression, that of the given matrix that we have at hand. Now from these eigenvalues we wish to determine or obtain the eigenvectors for the given matrix. We'll be doing that in the next page. Now as for obtaining the eigenvectors, what we do is we put those values of lambda that we have obtained in the matrix that has been provided, that is for the a minus lambda I, and we multiply it to the x, y and z terms, that is the basis, and equate it to 0, which is like this. So we put lambda is equal to 12 over here, and putting lambda is equal to 12, we get minus 2 minus lambda to be equal to minus 14, 5 and 4, and 5, and in this case we had let me see the other page that we have over here, that is 7 minus lambda. So 7 minus 12 is going to be minus 5 and then 5, and the last case obviously we know it's a symmetric matrix, so 4, 5 and minus 14. That multiplied to the basis, that is x, y and z, and that must be equal to 0. So using this equation, from the equations that we can get from this is minus 14x plus 5y plus 4z is equal to 0, and then we have 5x, so minus 5y plus 5z is equal to 0, and finally 4x plus 5y minus 14z is equal to 0. Now we consider these two equations, and from that what we get is for x we are cross multiplying the other two terms, that is 5, 5 and minus 5, 4. So 5, 5 is 25, minus 5 times of 4 is minus 20, minus of that is going to give me x over 45. For y we have y, and the other terms that we need to consider are minus 14 and 5 crossed 5 and 4. So minus of we take it the other way because the place value is negative. So we take it from the right diagonal, that is 5 times of 4 is 20, minus 14 times of 5, minus 14 times of 5, that is minus 70, that is over there. So this goes to y over 90, and for the last term z, similarly the place value being positive, we can just take the left diagonal first, that is minus 14 minus 5 is minus plus 70, minus 5 times of 5 is 25. So what we get over here is x over 45 is equal to y over 90 is equal to z over 45. So with those values available to us, so we have 45, 90 and 45, that essentially gives us the eigenvector to be 1, 2 and 1. So this is the first eigenvector that we are going to get. Now this is for lambda is equal to 12. Now for lambda is equal to minus 3, the other value that we obtain, we again put minus lambda minus 3 is minus of minus 3, that is this is going to be minus 2 minus of minus 3 is plus 1, 5, 4, you can use those values that are over there, 5, 10 and 5 over here, and finally 4, 5 and 1. this is multiplied to x, y, and z, giving zeros to the right, and this is going to give me x plus 5y plus 4z is equal to 0, and x plus 2y plus z is equal to 0, and finally we have 4x plus 5y plus z is equal to 0. All of that, and now if we choose the same method, we have x and the diagonal terms, we use these first two equations once again. So 5 minus 8 is a minus 3, and that is equal to y over, then y is taken to be negative, of course. So we take the right diagonal first, that is 4 minus 1 is 3, and as for z, we have 2 minus 5, that is going to give us minus 3. Now usually it's the case where minus 3, 3 and minus 3, we can just although we have it as minus 1, 1 and minus 1, it's rather easier to have 1 minus 1 and we keep a single negative. So this is the other eigenvector. Finally, for lambda is equal to minus 6, that is the last one, we put those values. Minus 2 minus lambda is going to be minus 2 minus of minus 6, so this is plus 6, so minus 2 plus 6 is 4, 5, 4 remain as such, 4, 5 remain as such, and we have the 4 over here as well. 7 minus lambda is 7, minus of minus 6 is 7 plus 6, 13, and these two terms are obviously 5, and we have x, y, and z to be equal to 0, and that yields the equation as because we are considering the first two equations only, so we need not be concerned about the third one, so we take the first two equations in place. That is 4x plus 5y plus 4z is equal to 0, and as for the second equation, 5x plus 13y plus 5z to be equal to 0. We need not be concerned about the third equation over here. So from this we have x over 25 minus 52, that is minus 27, is equal to y. Now that is 20 minus 20, that is going to give me 0, and for z we have it to be 52 minus 25, that is plus 27. So what we get from this is we're getting no, actually we are getting this as positive. So now that's all right. So we have this as minus 27, 0, and 27. That gives us minus 1, 0, and 1. So these are the three eigenvectors that we have obtained, that we were supposed to obtain for the given matrix that we had, the eigenvalues and the eigenvectors. We calculated the eigenvalues and then we obtained the corresponding eigenvectors. Up next in this question, we have to diagonalize the given matrix where we have A to be equal to 2, 0, 0, 1, 2, minus 1, and 1, 3, minus 2. The eigenvalues have been provided, 2, 1, and minus 1. So what we do here essentially is that, as we know, for diagonal of the given matrix, in order to diagonalize that, we have D, which is the diagonal matrix, will be P inverse AP. Now P here is the matrix which is formed out of those eigenvectors. Using those eigenvalues, we'll be obtaining those eigenvectors that we just did in the previous case as well, and with those eigenvectors we'll be forming a matrix which will be P. So the diagonal matrix is going to be P inverse times of A times of P. So that is how we wish to do that. So let's see. Now as for the eigenvalues, putting those eigenvalues that we have, lambda 1 is equal to 2, we put it over there, and so a minus lambda I, that is what we do, and we just subtract the lambda values from the diagonal parts. So we have that to give us 2 minus lambda I, which is 2 minus 2 0, and this is 0, this is 0 as well, and 1 2 minus 2 again for lambda 1 is equal to 2, that is equal to 0, minus 1 1 3 minus 2 is going to give me minus 4. If you can't really follow this, you can refer to the previous question for your understanding. And now this xyz is equal to 0, this is equated to the 0 column matrix, and what that gives us is, the first thing is obviously going to 0, and the first multiplication, that is, and for the second one we have x minus z to be equal to 0, or we have x to be equal to z, and as for the third case, x plus 3y minus 4z is going to 0. So because we have x to be equal to z, so this is minus so this is z plus 3y minus 4z, so minus 3z minus 3z plus 3y, we also have y to be equal to z. So what that gives us, if we are putting z is equal to 1, we are getting the eigenvector as 1 1 1, as simple as that. Now for lambda 2, we are using the value of lambda 2, which is 1, of course, and that yields 2 minus 1 is 1 0 0 1, and this is again 1 minus 1, and the last one is 1 3 minus 3, and that multiplied to x y z column matrix 0 0 0, this is a 0 column matrix, and then we have the first term, we have x is equal to 0, so that's solved. And for the next case, we have x plus y minus z to be equal to 0. Well, this solves everything because y is equal to z now. Now with x is equal to 0, y is equal to z, we can put z is equal to 1. We have this eigenvector to be 0 1 1. Now finally we take lambda 3 to be equal to minus 1, and from that we get this to be 2 minus of minus 1 3 0 0, this is also 3, this is 1, this is minus 1, and 1 3 minus 2 minus of minus 1 is plus 1, so this is a minus 1 in all. And this is x y z column matrix 0 0 0, and from this what we get is 3x to be equal to 0, which gives us x is equal to 0, and as far as the y and z relations are concerned, x plus 3y minus z for the second case is equal to 0, or we have y to be equal to z over 3. We take z is equal to 3, we get y is equal to 1, so we have 0 1 and 3. So this is the eigenvector. So with these eigenvectors we construct the matrix P, which is equal to 1 1 1 0 1 1 0 1 3. This is the matrix that has been obtained, and we will be requiring the determinant of it. So determinant of P that you can calculate by yourself, because there's only 1 in that first row. So this is 3 minus 1, that is going to give me 2, so the determinant is going to be 2. We require the determinant in order to obtain the inverse of the matrix. Now the inverse of the matrix, we'll do it in the next page. So in order to obtain the inverse, we need to consider the cofactors and then take the adjoint of it. So considering the cofactors of the P matrix that we have, the cofactor terms are to be presented over there. You can calculate the cofactors and check them. I have finished that in my rough work, so I'll be just giving it to you over here. So this is the cofactor, these are the cofactors that are present over here, and the adjoint of the cofactors is going to give us the, we take the adjoint of it, and taking the adjoint, what we get is 2 not, and this is -2, 3, -1, and over here -1 as well, and 1 and 0. So this is the adjoint. Now the P inverse matrix will be the 1 over P mod times of the adjoint of the cofactor matrix of P. So what we get is 1 over P determinant is obviously 2, and in this we have 2, 0, 0, -2, 3, -1, 0, -1, 1. Now the diagonal matrix is equal to P inverse AP. So P inverse, as we have obtained it over here, we are putting the value 1 over 2, 2 not, -2, 3 -1, 0 -1, 1. We put the value of A as well, A having the value 2 not, and there we have 1, 2, -1, and finally 1, 3, -2. And as far as P is concerned, we have 1, 0, 0, 1, 1, 1, and 1, 1, 3. We multiply this now. We keep the half for sure. Multiplying the first two matrix, we just end up with 4, 0, 0 in the first case, because that's all that we are going to get. -2, 3, -1, 0, 1, -1. In order to reduce the timing of the video, I have just used the rough work that I'm referring to the rough work that I have done. So this is the first two multiply to give this one, and the last one stays as such, and then we multiply that to obtain half of, obviously there is going to be 4 at the top, 4, 0, 0, 0, 2, 0, and 0, 0, -2. You can correct me if I'm wrong in some places, but this is coming out to be a diagonal, a very good diagonal. So this is obviously mostly the answer that we were looking for. We have diagonalized the matrix. This is the final diagonal matrix that we are looking for. Now there are other questions in the second part, part B. I'll be trying that in another video when time permits. Till then, thank you for watching.